So hi, thanks for the intro and thanks to the organizers for the kind invite. Today I want to talk about something that I think is both technically rich and practically overlooked in AI for scientific discovery, and that's the tails of multivariate distributions. By the end of this talk, I hope to convince you that in molecular design, it's not the average case behavior that we should be concerned about. It's the rare and extreme combinations of molecular properties where models fail and decision-making becomes fragile. I'll present two recent projects. I'll start with the new acquisition function for Bayesian optimization and then move to calibration. Both projects have a shared focus on modeling multivariate dependence and controlling tail behavior. In active molecular design, the goal typically is to find a molecule that's jointly optimized for multiple properties. And the properties may compete in the sense that improving one property leads to making another property worse. So the main challenge is to navigate an optimal trade-off among them. And here's an example of the property space of chemical compounds where the arrows point in the direction of desirable values. So they're pointing down and left if you can't see. And the bottom left panel shows a convex Pareto front where cell permeability and polar surface area compete. And when we consider multiple properties jointly, we start to notice dependence structures. Because of the complex, under biophysical processes that underlie all these properties, some of these properties tend to co-move in the center regions or in the extremes. And here it seems like permeability and polar surface area have tail correlations in this direction. On the other hand, if we think about LLMs, they are optimized for average case behavior. We minimize the average cross entropy across the training data. And also post-training, we often draw very few samples because it's expensive and sometimes just go with greedy sampling. And this can lead to suboptimal handling of rare events. We can formalize molecular design as multi-objective optimization. Actually, is the slide showing fine, or do you see a blank square in the middle? I'll assume it's showing fine. We formalize molecular design as multi-objective optimization that is jointly minimizing M objective properties over the vast space of molecules or molecule embeddings from an LM. And we'll assume minimization for this talk without loss of generality. If you want to maximize a property, you can minimize the negative of it. And more formally, we say that we minimize an objective function f that maps a molecule to a vector of M properties. And when f is a black box function like the wet lab measurement protocol, Bayesian optimization offers a sample efficient method for optimizing f. And BOtied works by specifying a surrogate function f hat that tractably and cheaply approximates f. It's common to do functional estimation with Gaussian processes. So you fit f hat to the data and get out the posterior distribution p of f hat given the data set D, where the spread of this distribution captures the model uncertainty. Okay, so pretend you can line up the molecules on the x-axis and you want to find a molecule minimizing one objective. The black dashed line is the true unknown function f. And so far, we have gotten lab measurements for 6 molecules, which are the black dots. We fit a flexible probabilistic model on the 6 data points to get out the green predictive distribution. And our uncertainty at the data points is near 0 because we've already measured those. And our uncertainty increases the farther we go from the measurements. So we get the green predictive distribution for every candidate molecule. And to decide which molecule to measure next, we use what's called the acquisition function. And this function takes a molecule and the predictions for that molecule, and then outputs a number, a score, where a higher score means the design is useful, so we should try to evaluate that. Essentially, the acquisition function balances exploration and exploitation so that we acquire designs for which F hat is highly uncertain about. So exploration kind of in this region, while also acquiring designs that F hat is confidently predicting to be the best. So exploiting here near the current minimum. And the MOBO algorithm proceeds in repeating cycles of first fitting the surrogate on our data set D, then running optimization to obtain the maximizer of the acquisition function, X star. And then we query the black box function on the selected design, and then append the pair to our data set. And then we go back and refit the surrogate on the expanded data set and repeat. We may query LMs in each of these steps, or we may have an end-to-end kind of agent. But we said F is a vector-valued function. So what does optimal mean when we are dealing with vectors in Rm? For this, we can define vector ordering in terms of dominance operators. So for two vectors in Rm, y and z, we say that z weakly dominates y, denoted like this, if all of z's components are less or equal to y's. So for m equals 2, y is here, and z that lies anywhere in the pink region, including y itself, would weakly dominate y. And strict dominance is a stronger condition where z weakly dominates y and doesn't equal y. So in case it's not showing clearly, we don't include y itself, so the circle around y is dotted, not solid. So in m equals 2, two properties, you can basically orient yourself like the more inner points dominate the more outer points. We said that in the multi-objective setting, objectives may compete and there may not exist a single optimal solution. And optimal points are instead defined in terms of the Pareto front, which is the set of points that are not strictly dominated. And here the green points are on the Pareto front. And we can see there's no other point that strictly dominates the green points. So there's no other point that is more inner than the green. And most often, the true Pareto front will be an infinite set of points. So for example, spanning the entire green line. And in multi-objective Bayes-opt, we typically aim to find a finite approximation, which we will denote p hat. So suppose we came up with an approximation set, p hat, for the Pareto front. To evaluate how good p hat is, we use what's called the quality indicator, which takes a set of vectors in Rm and outputs a quality score. And the popular indicator is the hypervolume of the polytope that's dominated by p hat and bounded from above by a reference point. This is the black square, which is often set as the worst possible solution of interest. So in 2D, the hypervolume is the shaded gray area. And as we obtain points closer and closer to the true Pareto front, which is indicated as a red curve, you can see that hypervolume would increase. HV is widely used, but the HV computation scales super polynomially with m because it involves an m-dimensional integral. And the computation gets very expensive with more than 4 objectives, 4 molecular properties. Another limitation is that HV is sensitive to the rescaling of objectives. And this is not desirable because nothing inherently changed about the molecules that we obtained, just the units that we chose to describe them with. At this point, hopefully we're on the same page with quality indicators and acquisition functions. We've talked about the HV quality indicator, which is a geometric quantity. We instead take a probabilistic perspective. Let's now view the molecules as random variables x and the property vectors y as random variables that are the result of pushing forward the molecule random variables x through our black box function f. And now let's think about the cumulative distribution function of y. You're probably familiar with the multivariate PDF, the probability density function. So for example, here is a bivariate Gaussian PDF for m equals 2, so for two properties. Now the CDF at y1, y2 is the result of integrating the PDF from negative infinity to y1, y2. And it tells you what fraction of molecules had the first property less than or equal to y1 and the second property less than or equal to y2. So exactly weak dominance. And because it's essentially a fraction, the CDF values are in the range 0 to 1. And this bottom panel shows the corresponding bivariate Gaussian CDF. And the bottom left is a plot we should get more familiar with seeing. It's a contour plot that horizontally slices the CDF at different values alpha from 0 to 1. And these are also called the alpha quantile or alpha level line of the CDF, which is the set of all the values y with the CDF value of alpha. It turns out that there is a theoretical relationship between the CDF and the Pareto front, which is that the Pareto front belongs to the alpha 0 level line of the CDF. To illustrate this, here I drew 200 points from a known distribution in gray dots. And the true Pareto front is the solid red curve. And then I ran kernel density estimation on the 200 points to get the PDF on the right panel. And if I compute the level lines of the corresponding CDF, we get the dashed lines in the left panel, and the alpha level lines converge to the approximate Pareto front as alpha goes from 0 to 1, so from yellow to purple. And the alpha 0 level line closely traces the convex shape of the true Pareto front. We use this connection to define a new CDF-based indicator. And the indicator, the CDF indicator of set A, which could be our approximation set p hat for the Pareto set, is the minimum of the CDF evaluated at each element of A, such that lower scores are better. And in our paper, we proved that the CDF metric satisfies weak Pareto compliance, which is a property that makes it useful as a metric. So say for intuition, A is the set of blue points and B is the set of orange points. If we compare A and B with the hypervolume indicator, the blue shaded area is greater than the orange. So we conclude A is better than B. Similarly, if we compare using the CDF indicator, the minimum CDF evaluated at the blue points, which is 0.3, is less than the minimum CDF of the orange, which is 0.6. So we conclude that A is better than B. And the CDF scores also induce multivariate rankings of these points, where the smaller CDF scores are ranked higher, or better, closer to the Pareto front. Now, we'd be getting nowhere in terms of speed if we first fit the PDF and then integrate it to get the CDF, because we'd still be computing a high-dimensional integral, just like hypervolume. So instead, we implement BOtied using Vine copulas, and it's very fast. I won't go into how copulas work, except to say that it has favorable time complexity that's up to quadratic in M. And this would address the first limitation of hypervolume, the issue of computational complexity. And we can incorporate any domain knowledge that we might have about Y into the CDF fitting. And so, for example, we may have some observations of Y that we can't use to train the surrogate model because we don't have the associated X pairings, but that can still inform the model choices for the Vine copula for constructing P of Y. And if we have reason to believe that the properties are smooth, then the model-based Pareto could be more robust, especially if the data set is sparse. Now we address the second limitation of hypervolume, the sensitivity to rescaling. The CDF indicator has a nice property of being invariant to any monotonic transformation of the objectives, which is a property inherited directly from the CDF. So on the left top here, we have molecules plotted in the original property space and colored by their hypervolume. And the 5 molecules that are shaded in gray are the top 5 according to HV. Now we squash F2, the vertical property, with the arctangent function, and then reevaluate the hypervolume. Based on the colors, we see that hypervolume is dramatically different, and that now it favors molecules with low F1, and it doesn't care about F2 because F2 has been squashed. We do the same thing with the CDF metric, and the ranking doesn't change. And this invariance property is very important for molecular design because we make linear and log-like transformations all the time. For example, molecular assay data often come in some form of rate constants like KD, which span very small values. So it's common to work with the PKD, which is a log transform that removes the tails. We don't want to be sensitive to uninformative transformations like this. We talked about the HV and the CDF quality indicators, and these are objects that score sets of molecules that we've already measured in the lab. So say the white circles here. The acquisition function is a very similar object that scores each molecule that's yet to be measured based on the predictions by the surrogate model that is shown in orange. And these are related objects, and quality indicators can be used to define the exploitation portion of the acquisition function. I'll skip the details, but basically the HV indicator can be folded into the expected hypervolume improvement acquisition function. And similarly, we can use the CDF indicator to formulate the BOtied acquisition function. And we named our acquisition function BOtied because the CDF induces multivariate rankings, and the molecules on the approximate Pareto front are tied in their rankings. Now moving on to the experiments, BOtied outperforms existing acquisition functions even when evaluated by the HV metric. Here, the x-axis is the iteration number, and the y-axis is symbol transformation of HV. It's basically the log of the difference from the ground truth Pareto front, such that lower is better. So lower is better for the y-axis. And the 2 shades of magenta are the 2 different versions of BOtied that differ in the way the CDF was fit. And QM Perigo in green is an acquisition function that takes the weighted sum of M objectives with random preference weights. So it's effectively single objective. Orange is the EHVI acquisition we went over, and the dotted black is the random Sobel baseline. BOtied also does well on a real-world cell permeability data set, and this is the long-tail molecular data set we saw in the very beginning. And the implementation with Vine copulas makes BOtied very fast. So as M increases, the wall clock time of HVI explodes, so does the joint entropy search, which is an information theoretic acquisition function. On the other hand, BOtied is very fast with large M and is competitive with Perigo, which is the one that scalarizes the objective, so it's effectively M equals 1. I'll let you read the summary in the interest of time. I'll just say that an interesting future extension of this is the differentiable BOtied, which would be useful for doing guided generation. And let me know if you'd like to collaborate. The second project I'll introduce more briefly has a similar flavor, but focuses on calibrating the surrogate model. Once again, the motivation is that molecular characterization involves many correlated target properties. So for a small molecule design, for example, we might measure over 50 properties, but these properties are highly correlated because they are the same kind of assay that's just repeated across different species. So we're in the business of doing multi-target regression, where we're given an exchangeable data set containing ordered XY pairs, where X is the embedding or some representation of molecules, and Y is the d-dimensional vector label. Conformal prediction is a very attractive framework for equipping any regressor model, even point estimators, with calibrated uncertainties. So say we choose miscoverage level alpha, and this is the fraction of times that we're willing to be wrong. Then the conformal procedure yields the prediction set gamma for a test molecule X star that satisfies an important property called marginal validity. Marginal validity basically says that gamma contains the true Y star with probability at least 1 minus alpha. And we'll assume alpha is 0.1 throughout the talk unless I indicate otherwise. And the conformal procedure is very simple. We'll just walk through the procedure for a single target, d equals 1. First, you split the labeled data into the proper training set and the calibration set. And then you fit any underlying predictor, f hat, on the training set. And the heart of the procedure is the nonconformity score, which quantifies the degree to which true Y does not agree with the predicted f hat of X. So for example, you can define it to be the absolute error. And you evaluate this on the calibration split. And if the calibration set has n data points, then you get out a distribution of n scores, which I plot on the left in blue. Then given the target miscoverage rate of 0.1, you compute the 0.9 quantile Q of the scores. And then this is the one marked in green. And we see that the quantile value is around 2. Then the conformalized prediction set gamma is defined as the set of Y for which the nonconformity score is less than or equal to Q. When this score is the absolute error, we can rearrange and get that gamma is the original point prediction f of X plus minus Q. And so at test time, we get gamma that is plotted in green. So for all test instances, we get the same sized prediction interval where each side of the interval has length 2. Now, what if we have 2 targets? Here are now the scores in blue. These are now 2-dimensional vectors. And a naive extension would be to just apply CP independently to each target. But then the quantile level that we have to extract for each target is no longer 0.9. It's actually more extreme than that because it's the product of the target specific levels that has to equal 0.9. So we need to work with something like the square root of 0.9, which is around 0.95. And as before, we would extract the quantiles independently for each target, and then these would define the size of the prediction set, which are now rectangular around the original point prediction. And as you can see, the prediction sets are huge. They almost span the entire property space. And as the number of properties D increases, this is only going to get worse. We end up with even larger quantiles and thus less efficient prediction sets. And often the calibration set may not be large enough to accommodate these extreme target-specific quantile levels. When the scores are correlated, which is likely when the properties themselves are correlated, modeling the targets jointly can yield more efficient prediction sets. And just like we did for BOtied, we modeled the joint CDF of the scores using a non-parametric line copula. And the estimated level lines are plotted in different colors here. And the quantile of interest then is the entire 0.9 level line of the vine, which is plotted in purple. And any point on this level line would work for conformal prediction. Here I've overlaid in green the quantile that you would get if you apply the procedure independently for each target. And there are points on the purple level line that have smaller norm than the green point and would thus yield more efficient prediction sets. So using vines for quantile extraction is one of our contributions. And another is the semiparametric inference angle. And in the interest of time, I'll omit the details. But the basic idea is that there is a simple correction that we can apply to the estimated quantile. And this involves an object called the efficient influence function, which is similar in flavor to the empirical influence function in the interpretability literature. So to summarize in pseudocode, our proposed modifications are twofold. We estimate the distribution of d-dimensional scores using the vine copula. And then once we obtain a quantile point from this, we apply the semiparametric one-step correction to further debias the quantile. Our method comes with theoretical guarantees. And we test our calibration procedure on a variety of tasks with d ranging from 3 to 16. And our underlying predictor that we used was a multitask lasso point predictor, but in the appendix of the paper, we also work with the conditional density estimator. Our coverage metric is the average fraction of the times that the prediction set contains the true test label. And marginal validity would require that coverage is at least 1 minus alpha. And as you know, the coverage can trivially be maximized to 1 by returning the entire RD as the prediction set all the time. So we also report the efficiency, which is the volume of the prediction set, such that smaller is better. Our baselines included the independent scheme that we covered in the beginning, where targets are treated independently, defining a scalar score as the L2 norm of the prediction error, and using the empirical score distribution instead of fitting a vine copula model. And then our proposed methods fit the vine and include the estimated quantile, both with and without one-step correction. I'll be a bit quicker and just say that in this slide, we show that one-step correction helps. And pink is our procedure using the correction, purple is without, and we see pink is closer to exact coverage than purple. And we see that fitting the vine copula is better than just taking the empirical distribution. And on various real-world data sets, our methods are valid and outperform baselines in efficiency. I'll just mention here that another benefit of estimating the joint distribution of scores is that we can natively handle partially missing data. You know, as D gets larger, chances are that we don't have labels for all D properties. So when missingness is at random, which means that missingness depends on the observations, we can't just take the fully observed subset of the data because that would result in a biased quantile estimate. So in the paper, we show that with the particular choice of the copula model, we can do missingness imputation. And this is actually a very common scenario in drug design. You know, for example, we may only measure target 2 after we measure target 1 and see that it exceeds a certain value. And it could be that target 1 is the important property like potency, and we choose not to expend lab resources on measuring target 2 for the molecule if it's not potent enough. I'll let you read the summary. And I should conclude. I just want to emphasize that modeling the tails can be very powerful. For standard Bayes-opt, the model comes in at the level of specifying a surrogate model that undergoes Bayesian updates as new information is acquired according to a predefined acquisition policy. And this surrogate model, the surrogate modeling of P of y given x is a multivariate regression task. And BOtied you can think of as introducing an additional model, which is for the population level distribution, P of y. And semiparametric CP similarly introduces another model for the population level errors, or the nonconformity scores. Both projects use nonparametric vine copulas to model flexible tail dependence. And this really gives us the structure that we need to explore regions that matter the most for drug design. So for those of you working within agentic or foundation model settings, I hope this angle can inspire new tools that have improved the reliability in the tails. With that, thank you.